Hey everybody, I'm sorry I cut the last lecture so short. Uh, Instead of hitting the pause button, I ended the recording. So this is lecture 4, part 2. And here's our example. Determine whether the system of conditions below is consistent or inconsistent. For the first condition, the diagnostic message is stored in the buffer or it is retransmitted. The second condition, the diagnostic message is not stored in the buffer. The third condition, if the diagnostic message is stored in the buffer, then it is retransmitted. So here are the conditions, A, B, and C. We don't have a D here. And what we don't have so far, but we need to find out, is what are the simple statements, P, Q, and R, that these conditions are made up of. Now I see one here. Here's a simple statement. The diagnostic message is stored in the buffer. It's a simple statement, and it's the first one that we see, so let's call that one P. So simple statement P, the diagnostic message is stored in the buffer. Okay. Now here's a simple statement. It is retransmitted. And what does the pronoun it refer to? The diagnostic message. So we'll let this be our second simple statement. We'll call it Q. So Q is going to be the diagnostic message is retransmitted. So we have the first two simple statements identified, and we've assigned them the lowercase letters P and Q. And since we pretty much have this first statement or this first condition diagrammed, let's just go ahead and take care of that disjunction. Or it's going to look like a V. So we have our first condition written symbolically. Now let's do the same with the second and third conditions and identify any other simple statements that may be in these conditions. Let's see. The diagnostic message is not stored in the buffer. Well, this is just the negation of P, isn't it? P says the diagnostic message is stored in the buffer. This says the diagnostic message is not stored in the buffer. So this is really not a new simple statement. It's just the negation of the simple statement P that we've already identified. So we'll call this thing not P. And now the next one. If the diagnostic message is stored in the buffer, then it is retransmitted. You know what? I don't see a new simple statement here. I see two simple statements, P and Q, that we've already identified. The diagnostic message is stored in the buffer. That's P. So we will label it as such. This is P. And then we have if, that is, the diagnostic message is retransmitted. That's the simple statement Q. Oops. So we have this third condition diagrammed except for the conjunction. And this is an if-then conjunction, a conditional statement. So we diagram that by having an arrow point from the first to the second. Son of a gun. We only had two simple statements here, and that's fine. This example will work just fine. Now I'm going to erase part of the board. So if you need to pause here and copy down anything that you haven't copied down, go ahead. But I'm going to erase these last two lines just to make room for what conditions A, B, and C are in terms of P and Q. So A, that is P or Q. Condition B is not P. And condition C is P implies Q, or if P, then Q. So symbolically, these are our system conjunction, our conditions. A, B, and C, these are our system conditions. And to see if the system is consistent, we're going to construct a truth table for the conjunction of these three conditions or statements. Okay, let's go. We only have two simple statements, so there's only going to be four sets of truth values, or four combinations of truth values of P and Q. So when we only have two simple statements, this is how we do it. On the outside, true, true, false, false. And on the inside, true, false, true, false. These are all of the combinations of truth values of P and Q, with no repetitions. So let's see, what do we need to do? You know what? I guess we can do any of these first, so just let's go A, B, and C in this case. A, P, or Q. This is an or statement or a disjunction. So what's the special case for an or? The only time it's false is when both statements are false, right? So you look for a case where both P and Q are false, and here it is. This is the only time that the statement P or Q is false. All the other times it's true, so we can fill in these other cells without even thinking. Now, the next statement, the negation of P. And tell you what, let me write down B here, negation of P. All this does is change the truth value of P from true to false. So P is changed from true to false, or from false to true. There, that was pretty painless. And our last condition, C, condition C is that P implies Q. This is an if-then or an implies statement. What's the special condition for, or the special case for the conditional statement P implies Q? The special case is if we have true implying false, then it's false. All the other times it's true. So this is false when we have P true and Q false. Now, when does that happen? Here's P true, here's Q false, and this is the only time that it happens. So we put false here. All of the other times it's going to be true. Now, is our system of conditions consistent? It will be if we take the conjunction of A, B, and C, and at least one of them, or if it's true for at least one combination of truth values of P, Q. So let's see, we want A and B and C. And what's the special case for a conjunction? A conjunction is only true when all of the simple statements that make it up are true. So does that ever happen? Let's look at A, B, and C. Are they all simultaneously true? C. B's false here, B's false here. Here we have true, true, true. So here, when P is false and Q is true, we have A true, B true, and C true. So right here, A, B, and C are true. That gives us a big fat true right here. All of the other times, we have at least one false. We have A false. We have B and C false here. We have B false here. This thing is false the other times. So this is the set of truth values for the conjunction of our systems, the conjunction of our conditions, A, B, and C. Now, what were we trying to do to start off with? Weren't we trying to determine whether or not the system of conditions A, B, and C is consistent? And it's going to be consistent if the conjunction of A, B, and C is true for at least one set of truth values of P and Q. And here it is right here. When P is false and Q is true, the conjunction of A, B, and C is true, this system is consistent. So this is our final answer. And this table is the work that we have to back it up. Hey everybody, we're back. You know, we haven't seen an example yet of a system of conditions or a system of specifications that's inconsistent. Just a hunch, maybe this one will prove to be inconsistent, but let's find out. And these look familiar, don't they? First thing we'll do, I guess, is just identify the simple statements that make up these conditions or specifications. The diagnostic message is stored in the buffer or it is retransmitted. So the first simple statement is the diagnostic message is stored in the buffer. Since that's the first simple statement that we see, we'll call it P. So P is the statement, the diagnostic message is stored in the buffer. Now let's move on. Or it, that is the diagnostic message, is retransmitted. So it is retransmitted. That's our second simple statement. So Q, it, the diagnostic message, is retransmitted. And we've identified the simple statements that make up condition or specification A. All we need to do is represent the connective symbolically. This is an or, a disjunction, so we represent it with that V. Onward and upward. The second condition or specification. The diagnostic message is not stored in the buffer. And this is not a new simple statement. This is a negation of P, isn't it? P is the diagnostic message is stored in the buffer. This is not P. The diagnostic message is not stored in the buffer. So there's nothing new here. We represent this with not P. Now to the third condition or specification. If the diagnostic message is stored in the buffer, then it is retransmitted. I don't see anything new here. The diagnostic message is stored in the buffer. That's P, isn't it? So I will just denote this with P. And this thing, it is retransmitted, it being the diagnostic message. That's just Q. The diagnostic message is retransmitted. So this is Q. So we have P and Q again, but joined together with a different connective. This is an if-then connective, a conditional connective. So we'll represent that with an arrow. And this reads symbolically, if P then Q, or P implies Q. So we don't have any new simple statements yet, but we do have a new condition or a new specification. The diagnostic message is not retransmitted. Is that new? Isn't this just the negation of Q? The diagnostic message is retransmitted. So nothing new here. This is just the negation of Q. So again, we have a system of conditions or a system of specifications made up of only two simple statements, P and Q. And that's fine. We don't want to get too complicated. But I will say that we will have some examples where our system of conditions or specifications is made up of three simple statements. Now, here's what I want to do. I'm going to erase the bottom two lines. Just, you know what? Maybe I won't. I need a place to write down what my conditions or my specifications are, A, B, C, and D. So condition or specification A symbolically is P or Q. That looks good. And condition or specification B, that's just the negation of P. Condition or specification C is P implies Q, or if P then Q. And then last but not least, specification D is not Q. So I'm going to keep those encapsulated and erase the rest of the board so that we can determine whether this system of conditions or system of specifications is consistent or inconsistent. Okay, here we go. We're going to set up a truth table for the conjunction of these four conditions or specifications. So the first thing we do is we fill in all possible combinations of truth values of the simple statements P and Q. True, true, false, false, true, false, true, false. And I guess we can go straight down from top to bottom. First we have P or Q. And you know what? I want to change that just a little bit because I also want to include the information that this is specification A. So A is P or Q. There we go. This is a disjunction or an OR. What's the special case for an OR? An OR is only true. No, let's see, an OR is only false when both statements that make it up are false. And that happens right here. P is false, Q is false. So this is the only time that P or Q is false. All the other times it's true. Now let's go to work on specification B, or condition B. Condition B is just the negation of P. And remember what that is? The negation just changes true to false and false to true. So in these two cases, when P is true, this becomes false. In these two cases, when P is false, not P becomes true. Okay. Next condition or specification is C. P implies Q. And this is an if-then, a conditional statement. We can also say P implies Q. The special case for this, the only time it's false is when we have what? A true implying a false. So we look for P true and Q false. Does that happen? Yeah. Right here it happens. This is the only time that it happens. P true, Q false. So under those conditions, it's false. For every other set of circumstances, every other possible combination of truth values of P and Q, this thing is true. And now our last condition or specification, D, and that's just the negation of Q. So not Q. And the negation operator just changes true to false and false to true. So if Q is true, like right here, not Q becomes false. If true is false, like right here, then not Q becomes true. If Q is true, right here, then not Q becomes false. And if true is false, like right here, then Q becomes true. Beautiful. We have all of our conditions or specifications mapped out here. Now we just need to do the conjunction of A, B, C, and D. A and B and C and D. And I guess we don't really need this anymore. It's a conjunction of 4 statements. The special case is that a conjunction is only false when all of the statements that make it up are false. Is there ever a time when A, B, C, and D are all false? Let's see. A is true here. And let's see. Wait a minute. Did I say that right? Did I say that right? I think I misspoke. I really do. The special case for a conjunction is that it's only true when all of the statements that make it up are true. An and statement, a conjunction, it's only true when all of the statements that make it up are true. So is there ever a case when they're all true? That's what we need to look at. And let's see. On the first line of our table, the conjunction is false. B is false here. On the second line, B is false here. On the third line, D is false. And on the bottom line, A is false. So in each possible set of truth values for P and Q, at least one of the statements, A, B, C, and D, is false. For example, when P and Q are both true, B is false. So the whole thing is false. When P is true and Q is false, both B and C are false. So again, the conjunction is false. When P is false and Q is true, D is false. And when P is false and Q is false, A is false. So the conjunction of these conditions or specifications is never, ever true, which means that this system of conditions or specifications is inconsistent. So here's our answer. Voila! Here's our answer, and here's the work that confirms our answer or justifies our answer. Next, we are going to do logic circuits. Back again. Here's our introduction to logic circuits. A logic circuit is a device, for lack of a better word, that receives one or more input signals in bit form and yields a single output signal also in bit form. The logic circuits that we study will be composed of one or more basic logic circuits that we call gates. And there are 3 of those. So let's look at our gates or our basic logic circuits. Okay, here are the 3 basic gates. This thing is called an inverter. And what it does is it negates the truth value of the input. So, if we have P is our input signal, then the output is going to be not P. And this is the only basic gate that we consider that has just one input. Here's the second input gate, the OR gate, and it has 2 signals per input. So we'll call those signals P and Q. And the OR gate takes the signals P and Q, and as output, it delivers the signal P or Q. And then finally, we have the AND gate. It has two signals as input, which we'll call P and Q. And as output, it has the conjunction P and Q. So those are our three basic logic circuits or logic gates. So take a look at these, write them down. All of our logic circuits will be composed of different combinations of these things. And just for the sake of example, let's work with each one of these gates, just using single bits as input. So we are now doing examples. Here's one example. And let's say that the input is the 0 bit. Logically, 0 stands for false. So the inverter is going to take false and convert it to true, which is the 1 bit. So this is how an inverter would act on a single bit signal. Now that we've done that, let's look at the other possibility. Let's have as our input the bit 1. This is our input, 1. And logically, this stands for true. So the inverter is going to change true to false, and that would be the 0 bit. Now on to our OR gate. We'll do a few examples with this. And let's just take 0 and 1. In other words, false and true. It's going to give us as output the OR of false and true. So if we have a false or a true, what are we going to get? A true, right? So this is going to give us 1. True. Now if we switch 0 and 1 here, let's look at a second example. Let's say we switch 0 and 1. So we have 1 here and 0 there. We still have a true or a false, and the OR of a true or a false is going to be true. So again, our output is true, or 1. For our third example, let's see what happens when we have both true. We have 1 or 1, which is true or true. The OR of two truth statements is going to be what? True. So here's our output. So far, we've considered 3 of the 4 possible cases, and they've all turned out to be true. So let's look at the last case. Let's say that we have 2 inputs, and they're both zeros, or false. We have the OR of false and false. What's that going to give us? It's going to give us false, isn't it? So 2 zeros in, 0 out. And that exhausts all of the possibilities with this OR gate. Now let's look at the AND gate. And maybe we'll just play the same game. We have 0 in and 1 in, so we have a false and a true. If we have a false and a true, we're going to get false, right? And that false is represented by the 0 bit as output. Now, does switching the bits change anything? Let's put the 1 up here and the 0 down here. Now we have a true and a false. If we AND a true and a false, what do we get? We get false, don't we? So we get 0 out again. Okay, let's try a third case. Let's put in as our input a pair of 1s. No, let's not. Let's put in a pair of 0s. So we'll have 0 and 0. If we take 2 zeros and do the AND, what's that going to be? It's going to be false, isn't it? False and false is false. This covers 3 of the possible 4 cases of zeros and 1s. And in each case so far, we've gotten 0 as our output. The only case that we haven't looked at is when we have 2 1s as input. So let's look at that. We have 1 in and 1 in, and this represents true and true. If we AND 2 trues, what do we get? We get a true, don't we? So this covers all possible scenarios with our basic logic gates. What we want to do now is look at some more complicated logic circuits that are made up of these 3 basic building blocks. Okay, here we have 3 input signals, P, Q, and R. And we want the output that's going to come right here. The first thing that happens is that P goes into an inverter. So what comes out the other side? If P goes into the inverter, the negation goes out, so this is not P. And as input to, what kind of a gate is this? Let's see. This is an AND gate, isn't it? So you know what? I'm going to write this down here. This is an AND. And our input signal up here is not P. And our input signal here is Q. And this is going to take the AND of these 2 things. So what do we get out here? We get not P and Q. And for our next stage, let's see, what kind of a gate is this? It's an OR gate, isn't it? And we have as input this R signal. And we also have this signal as input, which is not P and Q. So we're going to take the OR of these 2 things. So we'll get not P and Q. Or R. So this is our answer right here. Not P and Q, or